Welcome viewers to the third segment of the fourth lecture for the online series of lectures for the course of Algebraic Topology 2. In this segment, we will begin with the definition of a homomorphism, which we denote by del star at P, and it is supposed to be a homomorphism from HP of K comma K0. It's the relative pth homology group of K mod K0 to it's a group homomorphism from HP of K comma K0 to HP minus 1 of K0, which we denote by equation number 6. So and it is supposed to be induced by the boundary operator and is called the homology boundary homomorphism. Okay, so the construction of this operator of this homomorphism is as follows. Okay, so you will have an overview of how it works through a certain zigzag process now, but it will be done concretely later in this lecture. Okay, given a relative p chain of K mod K0 which we denote by Z. So given a relative p chain Z of K mod K0, okay, that is Z belonging to this group, one finds a chain one finds a chain D carried by K Z minus K0 satisfying so this is a class, okay, meaning that it is a coset CP of K0 because this guy is CP of K quotiented out by CP of K0. Okay. All right. This is a coset. This is equation number 7. Right? So when D is 0, it means that the identity element in the set of cosets is just Cp of k0, right? If in addition Z is a relative p cycle, of k mod k0, then del p of d is carried by k0. Okay, this follows from the definition of relative p cycle. Now consider the following inclusions, which are simplicial maps. Now consider the following inclusions, which are simplicial maps. So the first inclusion is of k0 in k, okay, because k0 is a subcomplex of k. Okay. And secondly, pi, it's the inclusion of the pair k comma the null, the null set included in k comma k0. So since they are both simplicial maps, we can think about the induced homomorphisms at the level of the chain groups. Cp of k0 in Cp of k, and the projection map pi hash at p, which projects Cp of k into Cp of k comma k0. So these are both induced chain maps. Okay. So this guy is a projection map, and this is the canonical inclusion. Now, given a relative p cycle of k mod k0, a relative p cycle z of k mod k0, that is z is in Cp of k comma k0, the chain d of Cp of k is a p chain on k carried by k Z minus K0 such that by hash at P of D is equal to Z. Okay, because remember that it takes Cp of K to Cp of K comma K0. So this is the guy D. So where did we wrote earlier, remember? The class of Z is equal to D plus Cp of K comma K0, sorry, Cp of K0. All right, so this guy is in Cp of K, which is carried by Kz minus K0, and this guy Z is an element in the relative chain group. Okay, so in other words, D is a representative of Z in Cp of K. So we see that D is the representative of Z in Cp of K. All right. Good. Now, since Z is a relative P cycle, Z is a relative P cycle, these things hold for relative P chain in general. Okay. Now we impose the condition that Z is a relative P cycle. P cycle of K mod K0 from equation 7, this was equation 7. From 7, it follows that del P of D, del PD is carried by K0. That is del PD is in Cp minus 1 of K0. Noting that I hash P minus 1 is the inclusion chain map, is the inclusion of Cp minus 1 K0 into Cp minus 1 K. This guy is the inclusion map. There exists P minus 1 chain C of K0 such that I hash P minus 1 C is equal to this guy, del PD. Okay, this is our equation number 8. Now, let me draw a commutative square. Cp minus 1 of K0 is included in Cp minus 1 of K via the inclusion I hash P minus at P minus 1, and Cp minus 2 of K0 is again included in Cp minus 2 of K via inclusion I hash at P minus 2. Then there is the boundary map delta P minus 1, and this is working in the complex K0, so that's why I put a superscript K0, and here this is delta P minus 1 superscript K. Okay, this square commutes. The diagram is seen to commute easily, and hence I hash at P minus 2 composed with delta P minus 1 superscript K0 is equal to delta P minus 1 superscript K composed with I hash at P minus 1. So, which means that I act the left hand side on the chain C, P minus 1 chain C, and also the right hand side, the operator on the right hand side on the P minus 1 chain C. This holds for P minus 1 chain C on K0. Now, this tells us that I hash P minus 2 del P minus 1 superscript K0 C is equal to del P minus 1 K composed with del P K D, right? Because of this, using 8 and the superscript del P, using 8 and the superscript in del pk means del pk is a map from Cp of k to Cp minus 1 of k. All right, and this guy is 0. We know that this is 0. This is the 0 operator resulting in 0 on the right hand side. So that we end up with, so this is a monomorphism, right? And hence this has to be 0. What we have inside the bracket is 0. So we get del P minus 1 superscript K0 acting on C is 0. Therefore, the P minus 1 chain C is a cycle of K0. We took that P minus 1 chain C of K0, right? And we end up with the fact that this P minus 1 chain C on K0 is actually a cycle of K0. I need some room. Let me raise this front part. I try to draw this diagram. So started with a cycle, right? Z belongs here. And then there is this projection map, which is pi hash at P, which projects Cp of K onto Cp K comma K0. And there is this boundary map, del P superscript K, that takes Cp of K to Cp minus 1 at K. And then again, there is this inclusion map we just studied, I hash at P, that includes Cp minus 1 of K0 into Cp minus 1 of K. And C belongs to this group, the group of P minus 1 chains on K0. So we have seen that if you start with Z being a cycle here, then we ends up with C being a cycle here. Let us now denote by C tilde a P minus 1 cycle that is not a P minus 1 boundary. P minus 1 boundary, meaning that this is a homology class, P minus in dimension P minus 1 of K0. So that C tilde belongs to H sub P minus 1 of K0. It's an equivalence class. Equivalence class C here. So by the equivalence class, I mean that there is an equivalence relation under which it becomes an equivalence class. It means that C tilde is equivalent to C tilde prime if there exists P chain E on K0 such that C tilde is equal to C tilde prime plus del P E. Okay. So if there is a relationship like this between C tilde and C tilde prime, we declare that C tilde and C tilde prime are equivalent. And so we, under this equivalence relation, we have a bunch of equivalence classes, and so C tilde is one such class. Okay. Good. On the other extreme, this is one extreme here. On the other extreme, let us denote by Z tilde a relative P cycle of K mod K0 that is not a relative p boundary of k mod k0. So that here as well, z tilde, the class of z tilde, is in the pth relative homology group of k mod k0. Okay, so it means that if z tilde is the class, is an equivalence class, with z tilde is equivalent to z tilde prime if we can write z tilde as z tilde prime plus kappa, with kappa being a relative p boundary relative of k mod k0, relative p boundary of k mod k0. Okay. Now it's time to define this map, the homology boundary homomorphism. Let me define it now. We defined delta star at P, which is a map from HP of k comma k0 to HP minus 1 k0 by delta star at P of the class of Z tilde to be equal to the class of C tilde. This is equation number 9. Now, we can state our basic theorem relating homology of k, k0 and the pair k comma k0. Okay, but before that we need the notion of the long exact sequence. A long exact sequence a long exact sequence is an exact sequence whose index set is the set of integers that is, it is a sequence that is infinite in both directions. It may, however, begin or end with an infinite string of trivial groups, okay? Infinitely many zeros, like trivial groups containing zero element only. Theorem 4. Let me check if it's theorem 3 or theorem 4. I think it's theorem 3, right? No, it's theorem 4. That's right. The exact homology sequence, the exact homology sequence of a pair let K be a complex, K0 be a subcomplex. Then there is a long exact sequence dot dot dot. The last entry in this row is HP plus 1 of K comma K0, and then from here we go on to the first entry of the next row, which is HP of K0, then it goes to HP of K, then it goes to HP of K comma K0, then from here again it goes to the first entry of the next row, which is HP minus 1 of K0, then to HP minus 1 of K, and then to HP minus 1 of K comma K0. And goes on like that forever. Okay, where I, okay, here I need to mention that HP of K0 is the map from HP of K0 to HP of K is the inclusion I star at P, and star because it's the induced homomorphism at the level of the homology groups. So when it's between the chain groups, we have the thing like the induced homomorphisms are denoted by I hash and pi hash. Okay, so this is pi star at P. And this guy is delta star at P. Delta star. So where I is the inclusion of K0 into K, and pi is the inclusion of the pair K comma null mapped to K comma K0 as discussed earlier. These are inclusions. And delta star at P is the induced boundary operator. Boundary operator or induced homology boundary homomorphism that we constructed or talked about a while ago. The homology boundary homomorphism. So there is a similar to this. There is a similar exact sequence in reduced homology, which is as follows. It's like this. HP of HP tilde of K0, and then it goes to HP tilde of Kn, which goes to HP tilde of K comma K0, and then it goes to H tilde P minus 1 of K0 and goes on like that. Okay, so for the rest of the section it will be the goal to prove this theorem, but before that I want to discuss a few examples. At least we should discuss an example which will show us how to apply this theorem to problems, okay, to solve problems, homological problems. Example 1. Let K be the complex pictured below. So this is the complex that we are discussing. Whose underlying space is the square here. And this is S4. This is S1. This is S2. This is S3. And all the two-dimensional simplices are oriented counterclockwise. This is sigma 4, this is sigma 1, this is sigma 2, and this is sigma 3. Okay. So the two simplices sigma i's are all oriented counterclockwise. So figure 2, this is the complex K, and the boundary of this complex is denoted by K0. Okay, figure 2, complex K and K0. The polytope of K is a square. We have seen in example 3 of lecture 3 of lecture 3 example in equation number 4 of lecture 3 that the relative homology group of K mod K0 in dimension 2 is isomorphic to the additive group of integers. This is what we have seen in lecture 3 of the course of algebraic topology. I think not in algebraic topology 1, I think in the previous lecture, right? Let me check for you. Example 3. Yeah, in this course, right? We have seen that the second relative homology group of K mod K0 is isomorphic to Z. The group H2 of K comma K0 is generated by, it's an infinite cyclic group, right? Is generated by the two chain gamma, which is the sum of the four elementary two chains sigma i's, I from 1 to 4. Sum of sigma i's where I runs from 1 to 4, where the elementary two chains corresponding to the oriented two simplices are all denoted by the same symbol sigma I. Okay. Now check that H1 of K0 is isomorphic to Z, right? And is generated by the sum of this elementary one chains S1 plus S2 plus S3 plus S4. So in the course of computation of H1 of K0, in the course of the computation of H1 of K0, one sees that, so when you do the computation, you will find that S1 plus S2 plus S3 plus S4 is nothing but 2 times, the D of gamma, right? Okay, when you apply del, the boundary operator here, del 2 gamma, right? So it's not D, it's del 2 of gamma. When you apply the boundary operators here, then everything will cancel out except for the ones lying on the boundary, right? So it goes like this, and it goes like this. The contribution here on this edge is cancelled against the contribution here along this edge. All the contributions cancel except for the ones lying on the boundary. Okay, so this is del 2 of gamma. Therefore, in this particular case, in this particular case, the boundary homomorphism, homology boundary homomorphism, del star 2 is a map from H2 of k comma k0 to H1 of k0. And these happens to be del star at del star of 2 is a map from Z to itself, which is an isomorphism. Okay, so let me write out the long exact sequence in this particular case. H2 of k and then to H2 of k comma k0, H1 of k0, and then to H1 of k, and this is del star 2. We can prove that del star 2 from H2 of k comma k0 to H1 of k0, we can prove that this is an isomorphism by considering the exact homology sequence, of the pair k comma k0. Let us focus on the following portion of the exact homology sequence. H2 of k to H2 of k comma k0, the ones that is written, the part that is written here, and then from H2 of k comma k0 to H1 of k0, and then from H1 of k0 to H1 of k, this part only. And this is delta star of 2. And for the particular example, H2 of k vanishes. And similarly, H1 of k also vanishes. So the exact sequence that we are looking at is as follows: 0 to H2 of k comma k0, to H1 of k0, to H1 of k, to the trivial group, because that also vanishes, and this is del star of 2. From the exactness of this sequence, one immediately finds that the kernel of del star of 2 is supposed to be 0. Therefore, del star at 2 is an injective homomorphism. Again, using the exactness of the sequence, image of delta star 2 is the whole of H1 of K0. So that del star at 2 is a surjective homomorphism. Is a surjective homomorphism, which implies that del star of at 2 is a bijective homomorphism or simply an isomorphism. Del star at 2 is a bijective homomorphism that is an isomorphism. Okay. I think it's a good point to take a break. We'll be back with the statement of zigzag lemma in the next segment of the fourth lecture. Thank you for attending the third segment of the fourth lecture.